Cool. So this week is graphs and graph algorithms. This is a very big topic, so we're going to be covering like a tiny fraction of it basically, just the very core stuff that'll come up a lot. But there's a lot more stuff that you can go and research on your own. I'll describe some of the key other areas that are a bit later that we won't go into now. But for now, the focus on the graph algorithms is mainly going to be different ways of traversing graphs and how to do them and in what situations. So first, just a bit of background on graphs, and also I'm trying to move the cursor out of the way. She hid, where's the, oh, there we go, yeah, okay. Is that gonna, yeah, all good. So yeah, there are different kinds of graphs. Hopefully that one up there is visible. But essentially what a graph is in terms of algorithms is a network of nodes and edges. So you've got nodes usually labeled with numbers 0 through to something, or in this case, starting from 1, and then edges connecting them. So there are different ways these can come together. They can be directed or undirected. So these two are both undirected because you can just go both ways between nodes with a connection. This one is directed because it's got the arrows, so you can only go one way. It's pretty self-explanatory. They can be weighted or unweighted, so that refers to the edges. So these two, the edges are unweighted here, so essentially they all have a weighting of 1, whereas this one has weights on the edges. And this can represent different things in different scenarios. The most common case is like if you think of these as like distances between each nodes. So it's 1 and 2 are essentially closer than 1 and 4 because it's got a distance of 1 compared to a distance of 3. There are different ways you can represent graphs in code. They're suited for different applications. There's 3 main ones, which are like having a class or a struct, some kind of object that represents each node, or an adjacency matrix or list. And I'll go through all of those now. So first, like a struct or a class. I don't have an example further than this because you'll almost never see this come up in practical use. It's really not very helpful to have it in this form. It's more so only going to be there if you're like storing it. I think the only time I've ever seen this kind of structure in competitive programming is like leak code questions, basically. Sometimes it might give you this node structure already defined and give you the input in that format. But if you're running any practical algorithms, you're generally never going to want to use this. So don't worry about it too much, but does anyone have any questions about that? It's basically just got the value or index of the node and then a list of all of the other nodes it connects to. And you can have a weight there as well. No, all good, cool. So this is an adjacency matrix, which you might have come across in like some of your maths courses. Basically, if you've got, in this case, there's 4 nodes, but I'm 0 indexing it to make it easier, so I'm counting it as if there's a 0th node that doesn't exist here. So there's a matrix of n by n, where there's n nodes, so in this case 5, counting that 0th one. And then the matrix, if it's an undirected graph, you just have 0s and 1s, 0 if they're not connected and 1 if they are connected, where each in row and column refers to a specific node. So like row 2, starting from the 0 index, so 0, 1, 2. Row 2, column, say 3, is 2 because nodes 2 and 3 have a weighting of 2 between them. Yes, like I mentioned, for an unweighted graph, it'd just be 0s and 1s, where 0 means no connection, 1 means there is a connection. For weighted graphs, generally you have the distances, so a distance from a node to itself is generally 0. The distances between these other nodes are just whatever's in the graph here, and then I've used x, which I've just defined, that's the maximum integer value you can have in C++. I'm basically representing an infinite distance. It's not practically infinite, but it is for our sake. Like in Python, you could use the inf keyword, etc. Yep, and another thing to note about adjacency matrices are that for undirected graphs, so because this is undirected, everything's two-way, it will be a symmetrical matrix, because if you go one row, then a column, it's going to be the same as going the column first and the row, so it doesn't matter which order you go between them. But for a directed graph, it won't be symmetrical. It can have different elements if you're on like opposite side of the diagonal. Does that all make sense? Yep, so adjacency matrices, definitely more useful than that like struct or just object from before, but it's still not very common. There's like, honestly, there's really only one main algorithm that usually uses adjacency matrices, which we'll go through a bit later. But the most common way it's good to represent graphs in code is with an adjacency list. And so in this one, it's a similar thing where you've got basically a 2D array of some kind, but instead of it being like a full matrix, it's got, I can't remember the actual name for this, I'm sure you went through an OOP, but all the lengths of the sublists are not necessarily the same, but each of these outer lists, so index 0 through to 5 represents a node. Again, there's a 0th node that doesn't exist here. I'm just pretending there is one, but because this is 1 indexed, usually they'll be 0 indexed. And then every element inside that list is basically a connection to another node. So 0th node doesn't exist, so there's no edges. Node labeled number 1 connects to the nodes 2 and 3, so those are in that list. Node number 2 doesn't have any outgoing connections, so that's empty. Node number 3 has outgoing connections to 2 and 4, and node number 4 has outgoing connection to number 3. And so this is an example of a directed one. Again, with an undirected one, this will basically, each edge will appear essentially twice in this list, one for each starting value or starting node, and one for each ending node. And this is definitely the most common way you'll see graphs represented in code, not necessarily on the inputs. Sometimes questions will often give you an input that's just a list of edges, but usually this is the format you want to convert it to, because that's how you're going to do most of the approaches. Yes, Magid?
So if it's a list of edges, how do I know which ones connect to each other?
I just went through that, but I can go through it again.
Oh.
Magid, I'm sure you know. But does anyone else want an explanation of that again?
It's like
Yep, Rory. So yeah, basically, if we look at node, say 3, the third index in this adjacency list, so that's 0, 1, 2, 3, that corresponds to this list 2 and 4. Those are the outgoing edges. So because 3 is going out to 2 and out to 4, that's why those are there. If it had a connection from 3 to 1, then 1 would also be in that list. Does that make sense? Cool. Is that good with everyone? Yep.
So would this only be useful for ones that are going with arrows?
Yeah, so it's easier to think about it in terms of arrows. For one of these graphs, what you can do is you can just imagine there's an arrow going both ways. And so if there was this connection between 3 and 4, essentially that is kind of like an undirected edge. So for an undirected graph, you just treat all of the edges like that, where they can go both ways. Yep.
What if it's weighted?
If it's weighted, what you can do is you can change, I'll have an example of this later, but instead of storing integers here, you can store a pair of integers. And so that's usually the easiest way to do it, where then each of these values, instead of just being the node it's going to, it'll be the node and the weight. Yep.
In some cases, do you need the ingoing arrows?
In some cases, it is good to have ingoing arrows, especially if you're doing some complex problems where you need to go in both directions and backtrack. But they definitely won't come up in any of the DIV stuff this year. And it's pretty niche scenarios. So I wouldn't worry about that until you're pretty confident with most other graph algorithms, but it does come up occasionally. Cool? Yep.
What's the benefit of using a vector over just a hash map where the values are?
Yep, so the general reason we use a vector is if you've got the nodes are labeled from 0 up to n, because then you know there's going to be n elements in this array. If you don't know what the labels will be, if they're just random integers, then definitely using a hash map, you can just kind of replace this to a hash map with a hash map to a hash map to an integer, which is a bit weird to wrap your head around. That is slower, so this is kind of preferred if you know what the labels are going to be ahead of time. But the hash map version is also useful if you want to immediately check if an edge exists. So if for some reason you want to know, is there a connection between nodes 2 and 3? With the adjacency matrix, actually, that makes it easy because you can just go to the element in the matrix and you can check immediately in constant time. With this kind of one, you need to do O of n in the worst case because you need to look through all of those edges. But if you use hash maps, then you can immediately go to the points in the hash map and check it.
Makes sense.
Yeah, cool. Any other questions? Great. Okay, so, there we go. So first algorithm going through is DFS, which stands for depth first search. So this is kind of probably the most basic way you can traverse a graph. And essentially what it does is it explores as far as possible in one direction before reaching a dead end, and then it backtracks. And usually you maintain a set of nodes you've already visited, so you don't accidentally go to the same node twice and get into an infinite loop. So hopefully this is visible. It's not great against that background. But if we start at, say, node 1, then we can go the order of depth first search traversal. There are a few different orders you can do. Whichever node you go after 2 is kind of just depends which one comes first in your adjacency list. But one way you could do it is you go 1, 2, 3, 5, 4, 6, and then there's no new nodes from there, so you go back to 4, no new nodes, and you kind of go back all the way up. In this case, you can explore the whole thing in one go, so you won't actually have to backtrack and explore a new branch. But say 2 had another node out here, then you could go do that same thing. It would backtrack all the way back here and then explore this one. Does that make sense? Where you're kind of going as far as you can until you run out of nodes and then stepping back? Yep. And so because of that kind of backtracking approach, a nice way to implement it is recursion. It's a very simple way to implement it. The issue with that is sometimes if you've got a very large input, you could run into stack overflow errors, in which case you can also just keep a manual stack because recursion is basically just a way of automating handling stack. DFS, it is very simple to implement, but it's not actually very useful for a lot of scenarios. The main things are like it's easy to detect cycles with DFS because you can already keeping track of what nodes you have. You can easily check if a path between nodes exists, but kind of more complex applications aren't really suited to DFS. Time complexity I've also noted here is E plus V, where E is edges and V is vertices or nodes. Generally, because in the worst case scenario, if you're exploring the whole graph, you'll have to visit at each vertex at least once, and you have to check each edge at least once. So it's kind of common sense. This is an implementation of it that I had. So this is the recursive implementation. So I've got this DFS recursive function up here. This is just my adjacency list. And before starting the recursive function, I've just declared this hash set visited, just to keep track of the current nodes that we've seen before. So then in the recursive function, I'm passing through my adjacency list and visited just by reference, so just so that I have access to them inside that function. They're essentially acting as global variables here, if that makes sense. But then I start at node 1, I'm passing in. So starting at node 1, I add it to the set of visited nodes. And then for each neighbor in the adjacency list, so we're going to node 1, that's this one, so then we're looking at each outgoing connection, so all the nodes it can go to next. If we've already seen it, then I'm saying return true. So in this case, I'm checking if we've got a cycle, essentially. So check if we've seen the node. If we have seen it, then we found a cycle, so we can immediately return true. If we haven't seen it, we want to do DFS on that node and keep exploring further. So that's what this is, and if that returns true, then it means we found a cycle lower down, so returning true there as well. If we get through everything and nothing's returned true, then it means we've reached the end, we've explored everything, we haven't seen a node we've encountered before, so I'm returning false because there's no cycles. This is, you would not necessarily always going to be looking for cycles, but that's one kind of just a simple application of DFS. Although this will only work for undirected graphs, because with the directed one you could have two edges going to the same node, which in this case you have to be a bit more careful, because cycles are a bit tricky to spot there. But does anyone have any questions about that? Cool. So that's the recursive application or implementation. This is using a stack. So if you have Stack Overflow, generally this will be the next way to overcome it. So instead of having that recursive function, you just have to manually declare a stack. So in this case, I'm still starting at 1. I'm adding it to the stack and to the visited array. And then while the stack is not empty, so while we've still got nodes left to explore, I'm taking the top node from the stack and then removing it from the stack. Again, going through every neighbor. If we've already seen that neighbor, it means we found a cycle, so I'm just printing that. If we haven't seen it, then adding it to our visited array and pushing it to the stack, so it's the next thing to explore. Because remember, when you push to a stack, it goes on top, and then when you pop from it, you take off the top. Does that make sense? Yep. So it's very similar. You're just kind of replacing that recursive call with this stack push and stack pop. So yeah, DFS, it's a nice simple one, but it's generally not too useful. And also one thing I forgot to mention, I think, is that DFS only really works on unweighted graphs. For weighted graphs, I mean, it will still work, it's just the weights won't be taken into account, so it's not going to be that useful for a lot of problems that involve weighted graphs. The other main algorithm on unweighted graphs is breadth first search. So as opposed to depth first search, we're going as deep as you can before backtracking. Breadth first search is you're kind of exploring one layer at a time, trying to stay as close to your starting point as possible. And so again, you still maintain a set of visited nodes. It's basically just DFS, but instead of a stack, using a queue. Because if you remember that ordering, instead of pushing to the top and taking it off, you're pushing to the queue and then taking from the front of the queue. So instead of going that, just keeping exploring, you're going one at a time outwards. I'll explain it on this graph in a second. But BFS is a lot better for DFS for a lot of problems because it's a natural way of finding the shortest path between nodes in an unweighted graph. So if we think about the way that the BFS traversal would work here, starting at 1, 2 is the only option. And then, so we got options here of either 3 or 4. So it doesn't matter which one first, but we got this queue. So we'd essentially be pushing both of these to the queue. Let's say it was 3 first, we go to 3, push 5 to the queue. And now the node currently at the front of the queue would be 4. So then we jump over to 4. We've already explored 5, so we don't need to add that, but we haven't explored 6, so we push that to the queue. Next on the queue was 5, so we do that, then there's no new nodes, and then last on the queue is 6, so we look at that. And so because we're kind of doing that queue that's like adding each node one layer at a time, every layer is always going to be clumped together with all the nodes the same distance from your starting point. And so that's an easy way to find the distance between, say, 1 and 4, because you get there after 2 iterations, essentially, in that queue. Again, O of V plus V for time complexity, because you have, in the worst case, you're checking every node and every edge at least once. This is the implementation. So it looks very similar to DFS, the stack way, but instead of a stack, we've got this queue. I'm also, instead of using just a queue of integers, I'm using a pair of integers here to represent the first number is the node, and the second number is the distance. You can also do it with just storing the node here and not the distance if you have like a marking value or a sentinel. Say like -1 is a common one. If you push that to the end of the queue after each like layer, because then after each layer is like when the distance increases, if that makes sense. And so once you reach the -1, you can increase your distance and push it back to the end of the queue. That's kind of a shortcut. I generally prefer this way because it's a bit more intuitive, but yeah.
You mean the distance from the first node?
From the first node, yes. Yeah, so same thing, similar with DFS, where you got this while loop while there's still elements in the queue. We're looking at so you're just taking the top of the queue or the front of the queue, so which is the current node and the distance from the first node. Looking at each neighbor, if we've already seen it, if it's in our visited array, or if it's not in our visited array, sorry, then we're adding it to the visited array and then we're pushing it to the queue. Because of this new node is a distance of 1 further away from the origin, then we're pushing the neighbor with the current distance plus 1. And it's never going to be back like close to the node because we've already processed that, if that makes sense, because it's always going outwards. Does that make sense?
Just a question.
Yep.
So if you did BFS on the graph insights, how does it know to go to 4 or 3 first?
You usually use an adjacency list here, so that just depends which one comes first in your adjacency list. It doesn't actually matter for the distance because they're the same distance away, but
Whichever way the thing's coded?
it's whichever way it's coded and which way you add it to the code. So I had the example back here. I think this was a different graph, but like say it was running on this graph, it would go to 2 first instead of 3 if it was at node 1, just because 2 is first in that list, and you're just iterating through that list in order. But it doesn't matter which way around these elements are, it'll give you the same result. Any other questions about that? Yeah, and so then I'm just saying if current is 6, so once we get to node number 6, I'm just printing the distance. So I didn't put the output on here, but the output would be 1, 2, 3, because it's 3 steps away from 1. Does that make sense? Yeah. So shortest path, that's good for unweighted graphs, but it's not going to give you the shortest path for weighted graphs because it just gives you the number of essentially steps. It doesn't sum up the weights or anything like that. So there's a lot of ways to find the shortest path in weighted graphs. Some of them are quite complicated, so I'm just going to go into 2 today. The first is Floyd-Warshall. The Floyd-Warshall algorithm is nice because it's a very simple algorithm to find the distance between every pair of nodes in a weighted graph. In this case, I'm counting the distance as just summing up the weights that you're traveling along. There are different ways you can measure distances, and most of them can be applied to the same thing. You just need to change the way you're calculating that distance, calculating the distance essentially. This only works if there are no negative cycles in the graph. So what I mean by negative cycle is if you imagine this 3 was -3, basically what you could do is you could go, actually I don't think it's possible in this example, but if you imagine like this was a weight 0, you could go -3 plus 2, 0, and you would end up 1 below where you started, and you've got like an infinite cycle to get infinite negative distance. That doesn't come up in a lot of problems, so you don't need to worry about it too much, but it's something to note that Floyd-Warshall will not work in that situation. But it will work on negative edges, as long as there's no cycle with an overall negative value. And it's O of V cubed, where V is the number of vertices, so it's pretty slow. That's the main downside of it. It's really simple, but it's quite slow, and the adjacency matrix is also uses a lot of space because you need an entry for every pair of nodes, even if there's no connection between them. The reason why it's O of V cubed is very obvious when you look at the code, because it's literally just 3 for loops. And so it's a very easy thing to implement, which is it's the nicest thing about it, really. So here I've got my adjacency matrix from before. I haven't got it here, just out of space, but so n's the number of vertices we have. And then we've just got 3 for loops. What they represent is k is kind of an intermediate step when you're getting from one node to another. And then I and j represents like every pair of nodes you're wanting to go from the start to the end. So essentially I is the starting point, j is the ending point, and k is an intermediate node. And if you know about dynamic programming, you don't need to worry about it if you don't, but it's basically using dynamic programming to check for every pair of nodes I and j, starting at I and ending at j, can I get there with a shorter distance by going through node k? And so that's what this if statement is. It's basically saying if there is a path between I and k and between k and j, x, remember, I was just setting to be like an infinite distance. So if they're not infinite distances, if there are actually connections there, then we want to update the path from I to j to be the minimum of these 2 values. So the first one's just itself, so we don't want to make the path bigger if there's not a shorter path available. But if there is a shorter path available, which is the distance from I to k plus the distance from k to j, so that's really just the path going from I to j through k. If that distance is shorter than the current distance we got from I straight to j, then we just update that. And it's very simple, and it's kind of hard to really wrap your head around it if you think too deeply about it, but the good thing is it's just got a simple overall intuition. It's very easy to code up even if you don't fully understand it. And then this code I've got to print the adjacency matrix afterwards. So I ran it on this graph. Again, I used a 0 node that doesn't exist, so the distance between 0 and every other node is infinity because it doesn't exist. But then for these main 4 nodes, we got these are the distances between every pair of nodes. So like the distance between, say, 2 and 4 is if we go 0, 1, 2, 4, so that's 4, because the shortest path you can get is like through 3. And so that's a very simple example, but this will work on graphs of any size. The issue is just it can get quite slow because of that v cubed. Are there any questions about that one? Yep.
Sorry, I may have missed it, but why do we need the 0th node?
The 0th node isn't necessary. It's just really nice because like I'm using an adjacency matrix, so since the lists are 0 indexed, it's nice to be able to say, okay, node 2 is at index 0 in that list. If we started at node 1, we need to like offset everything by like -1 so that the first one's at 0. I'm just ignoring that fact by adding an extra node that doesn't exist and never using it. Does that make sense?
Yeah, could you start the search from column 1 to row 1?
Yeah, so in this case I could, because since I'm not using that 0th node, I could change everything to 1 for this case. Although if you don't add that node and just set all of these, if you essentially -1 from the index of all of these, then you'd start from 0. Cool. Any other questions? Great. Okay, then the last one is probably the most common graph algorithm you'll come up for finding a short path. It's also the most complicated of all the common ones, which is a pain. But you probably heard of Dijkstra's algorithm, which is it's a very nice algorithm because it's quite fast. It's essentially the fastest way of finding the shortest path between any 2 nodes in a weighted graph. I've got a different picture here just because I couldn't find a good example to work on. This one's a bit hard to see. It's a shame that they've all got that background. But yeah, so Dijkstra's algorithm again works on weighted graphs. It's a bit more restricted than the Floyd-Warshall one. The Floyd-Warshall does work on negative edges if there's no negative cycles. This just doesn't work on negative edges. If there's negative edges, never use Dijkstra's. Yes?
What would even when would you ever even have negative edges?
Yeah, so if it's like a physical distance, of course you never have edges, but if you've got like some kind of cost function, like this is a lot more abstract, but say like you've got a cost function, you're trying to minimize the cost, and there's like ways you can reduce the overall cost, that could be represented as a negative edge. Yep, is that all? Yep. So yeah, only zero length edges will work here, but 0 or positive, it generally will be positive. So this doesn't come up too often. If you do have negative edges, Floyd-Warshall, if that's too slow or there's negative cycles, there is another common graph, weighted graph shortest path algorithm called Bellman-Ford, which you might have heard of. It's more complicated than any of these two, so I'm not going through it today. And you also almost never need it because Dijkstra's is faster and will work on almost every graph because like that example, like you almost never get negative edges. So yeah, shortest distance generally between any 2 nodes, but technically it does go from 1 node to every other one if you need that. It uses an adjacency list, not an adjacency matrix, and the time complexity is very implementation dependent for Dijkstra's algorithm. So you need to be careful there, but generally it's about E log V, where E is the number of edges and V is the number of vertices. I'll explain that when I get through the code here. So the code is a bit complicated. Hopefully it's not too bad. The good thing is you can have this on your notes in competitions, so that makes it a lot easier. But again, so we've got our adjacency matrix, n's the number of nodes, and so we start off by initializing this distances array. So distances, I'm initializing to integer max, or I could use that, if I still had x defined, you could use that. But this essentially represents the distance from the starting node to every other node. So in this case, I'm starting at 0, which is what I put here. So that's why distance is 0 equals 0, because the distance to itself starts at 0. But every other node we assume is infinitely far away to begin with. This looks like a bit of an abomination. It's simpler in other languages, but because the way C++ does priority queues, it's a bit of a mess. But Dijkstra's is essentially, it's a greedy approach where it always takes the shortest, it looks at the next node that we can get to in the shortest distance. And so it uses a priority queue to find which node that is. And unfortunately, the way to declare that in C++ is a bit ugly. But what I'm saying is that it's essentially a priority queue of pairs, because I want to keep track of both the distance, which is the priority value, and the actual node value itself. So a priority queue of pairs, this is what the underlying data structure is. So it's just using a vector, just keeping them in a list. That one doesn't matter too much for our purposes. And this is the comparison function it's using to determine which one has the higher priority. And so greater basically means that it's always going to use the shortest cost, which is a bit counterintuitive. It's just one of those things you need to either look up in the reference or put in your notes or remember. But essentially, it's comparing every pair. Pairs default to comparing their first value. So where the first value is that distance, it's always going to give the highest priority element is the one with the lowest distance. That's essentially what that declaration is doing. Does that make sense to everyone? Yep. So starting at node 0, so pushing that to the queue, node index 0 with element number 0. In this case, we don't have to worry about that not existing 0 node because this graph actually does start at 0. Distance from 0 to 0 in the array is 0. That's all set. Then similar to BFS, we got this while loop while we still get elements in that priority queue. We're looking at the element with the highest priority, and then so priority, and then the actual element itself, current, removing it from the queue. This isn't really necessary. It's kind of optimization where if the priority, so that's what you're currently looking at. If it's bigger than your current distance array, you can just ignore that node because basically the only time this will come up is if you've already seen that element before and you've set this distance to be a smaller value, but then there's just like an extra node left in the queue, so you can just kind of skip over that one. But this is the bulk of it, where for every node in that adjacency list that's connected to your current one, and so this is a case, I don't have a picture here actually of the adjacency list, but this is the case where you've got a weighted graph. So I've got an adjacency list containing pairs. So it's both got the next element and the weight of that connection. But for every connection, we're looking at if the distance to the current node plus that weight going to the next node, so this is the cost, if that's smaller than the current best distance to get to that next node, then we're updating that distance and also pushing that to the priority queue. And so at any time, the priority queue is basically going to contain a bunch of nodes that you could go to next and the total cost of going to them, and it's taking the lowest cost one. So basically greedily going to one node at a time until we've reached all of them, in which case this priority queue will become empty because you're not going to push it if the distance is bigger. And then we're left with this distances array, which has the distance to every other node. So this is the result for this graph, starting at 0. So distance from 0 to 1 is just 3 directly. The distance from 0 to 2, the best one is going through 1 and then to 2, which is a total of 4. The best distance to 3 is a bit hard to see. This is node 3. So going to 7, going straight through this node is a distance of 7. So that's not great. The best one is 6 because you can go 3 plus 1 plus 2. So that gives you 6 total. And then for this one, the best is 8, which is going straight here because the other way you could go, really the only one that makes sense would be like you go 6 to here, then plus 3, which is 9. So just going there directly through the 8 is better. Does that output make sense? Yep.
So when it says from going from 0 to 2, what the code does is it goes to 0 to 1 and 0 to 3, and then it compares them, pushes both 3 and 7 into the priority queue, and then it pops out top, which is the lowest value, which is 3. And
Is that start when you're at which node? Is that?
So if we're going from 0 to 2, right?
Yeah.
It can go to either 4, 3, or 1, right? And then the
Yep.
points on them are 8, 7, and 3. So it pushes all 3 of them into the priority queue.
Yep.
And then it just pops out it gets the top one, which is 3, which is the smallest one, and then uses that for the next
Yeah.
equations.
Yeah, so I'll run through that again just for everyone. But so we're starting at node 0. What it's going to do initially is that's our one we added to the queue, so it's going to pop that one, and then it's going to look at every edge. So 1, 3, and 4. It's going to add all of those and their total distances to the priority queue, so 3, 7, and 8 are the distances. The best one so far is 3, so it takes that one out. That's node 1. It's already updated that value in the distance array, so we've kind of set that in stone. That's the shortest way to get to 1, because there were no other paths that we could have taken that were any shorter. Then it looks at every outgoing node, so going back this way is a distance of total of 6 to get to 0, because you're going 3 plus 3. That's worse than the current best distance, so it doesn't add that to the queue. But then it could go here, which is 7. This is the same as this one, so it won't add that to the queue because it's a strict inequality here. But this way is a better way to get to 2, because currently 2 is like infinity, because we haven't seen it yet. So it'll add a distance of 4 to get to 2. The next best one we got a distance of 4 to get to 2, 7 to get to 3, and 8 to get to 4. So currently 4 is the shortest distance we can go to a new node. So then it'll go to 2, again going backwards increases it, so it won't do that. But it'll add this one because that's a total distance of 6 to get to 4. So then we look at the queue. The queue's got 6 to 4, 7 to 4, and 8 to, that's 3, I can't see. 7 to 3, 6 to 3, and 8 to 4. So there's actually 2 different elements in the queue that are going to 3, just kind of because this long one at the start is kind of outdated right now. And so what's going to happen is first it's going to do that lower priority one, which was a total distance of 6. It'll see that there's going to anywhere with all these nodes we've already seen before with the shortest distance, so it's not going to add them because it'll be longer than the current recorded one. I'll just finish this quickly. The only new one it could try is like here, but that's a total of 9, which is worse than the current 8, which is our best one, so it's going to ignore that. So it won't add any new ones to the priority queue. Now, still left in the queue was the 7 to get to 3 and the 8 to get to 4. So the 7 to 3, it'll do that one, but because of this thing, we've already been there on a shorter path, so it's going to skip that and ignore it. We've already done that. And then it'll do the 8 to 4 and record that in the array. That's basically done. Yes?
So that output is from node 0 to all the other nodes. So
Yeah.
if we were wanted to start a different node, would you just push in a different number?
Yep, you just push in a different number at the start and make sure to set distance of I, whichever node you start at, to 0. Because, this is essentially representing the distance from whichever node you pick to every other node. That's the only thing you have to change in this case. Any other questions about it? Cool. And that's pretty much it. So I haven't interspersed exercises between them all because the main challenge with graph algorithms is generally A, establishing your problem in the context of a graph, and B, figuring out which one to use. And then there's also, a lot of them are very similar, but you also generally don't need to do them by memory. You're going to have examples in front of you on your notes. And so I just wanted to I mixed all these up. These aren't in the order that I've gone through them. So have a go at least trying to figure out which algorithm you think you need to use. I'll be around to help. Other people in the community will be around to help. And just have a go at seeing if you can solve any of these. I'd strongly recommend starting with the easies. I think the easies are all just going to be unweighted graphs. But if you want to have a crack at some of the other ones, especially Dijkstra's and Floyd-Warshall, some of those will be in the mediums. Some of the mediums are also unweighted graphs, but they're a bit more complicated.